All right, welcome back. So we ended the last video with a binomial distribution, and we wanted to know how could we make a nice curve that makes it continuous in the same way that we took a uniform distribution and made a nice continuous distribution for it. So here's our binomial distribution, and actually let me back up a little bit. What we're about to work with doesn't have to be for binomial distributions, right? Binomial distributions gave you the likelihood of getting a set of results out of so many attempts, so many trials, probability of individual successes. Let me go ahead and pump the brakes on that. You don't need binomial distributions to talk about normal distributions. In fact, there are so many things that are normal distributions that we just call them normal, right? The pun that I've been accidentally making so many times this video series is that we call them normal because it's what normally happens, right? You talk about blood pressures, we found a normal distribution. We talked about heights, we found a normal distribution. Weights, normal distribution. So many things that are data driven form naturally a normal distribution. And so it's this nice gentle curve. Well, it starts general. It has an abrupt uptick once we get closer towards this peak. Remember, the peak would be the mode. For us, it's also going to be the mean and the median, but that's for a normal distribution. And then it's going to have a sharp decline as we get away from the mean, and then eventually go out far enough away, say 2 or 3 standard deviations, especially 3, there starts to be a whole lot of nothing out there. There's very few outliers, very few data points that are more than 3 standard deviations away. In fact, very few more than 2 standard deviations away. And that's going to form a normal distribution. So you're wondering, how do we make this curve? Right? To make the uniform distribution, we just averaged out the probabilities. We had a nice little graph to do that. Well, the math behind the probability density function, or the curve that we use to make a normal curve, is a little hairier. You got the E in there. E is a constant. Let's see here. We got X. X is just the number that you input. Mu, again, is the mean. And sigma is the standard deviation. Pi, of course, is the other big constant. E is about 2.7. Pi is about 3.1. I keep going, but I don't have 5 minutes in these videos. So really, every normal curve depends on X values, mu, and sigma. And I want you to notice before I click this link, those are the exact values that we use to make a z-score. So really, every normal curve we play with deals with z-scores. And that's very important going forward. So here I've retyped this same equation to make a normal curve. I've had to use A and B instead of mu and sigma because Desmos doesn't really like Greek letters. It gets kind of mad at me. But I want you to notice something. When I slide A around, when I change mu, when I change the mean of my data set, all that happens is the whole thing will shift up or down. That's all that will happen there. Next up, if I'm changing B, which B on Desmos anyway, when I'm changing my standard deviation, when I'm changing sigma values, what do you think will happen when I increase B? Will it get higher, shorter? Will it spread out? Will it get tighter in? Well, what happens if I increase B is the whole thing flattens out. Whole thing flattens out. And you should expect that, right? B is standard deviation. Variance, it talks about how dispersy it is from the data, from the center of the data. Higher standard deviation, more spread out. Lower standard deviation, less spread out. And the mean, of course, just shifts that up and down. And that's going to be how we make standard deviations. And because everything depends on just those two values, I want you to recognize something. Every normal distribution that we will work with is statistically similar. They're not geometrically similar, right? They have some that are tall, some that are skinny. They're not geometrically similar, but they are statistically similar. You give me mu, you give me sigma, I can tell you everything about that curve. And that's what we're going to do for the next bit.